As a scientist, what happens if your equations don't quite match up? You know you have something missing, but you can't figure out what it is. That's right. You create an entirely new form of matter, fill the universe 95% up with it, and spend the next century or so trying to find it. Dark matter and dark energy are mysterious, and as such they seem to be the go-tos for science fiction, along with the word quantum.
Captain's log, stardate 44932.3. The Enterprise is preparing to enter the Mare Oscura, an unexplored dark matter nebula.
For this highly controversial mission, you'll be towing the Juan Valdez, an orbiting supertanker full of rich Colombian dark matter.
Dark matter is a miraculous thing. With gene splicing, I can use your dark matter samples to negatively charge Romero's blood.
So what could generate an EM field large enough to get its attention, but still not show up on sensors?
An energy burst from a pulsar, a neutrino cloud.
Dark matter.
The two mysteries make up about 95% of our universe. Stars, planets, black holes, nebulae, neutron stars, all of them just make up a little 5% sliver. So it's obvious that these are huge. However, there is just one small problem with the theory of dark matter and dark energy. We can't find it. Any of it. But if it makes up 95% of our universe, why would it be so hard to find? So both dark matter and dark energy have been theorized to help with our understanding of the universe. For example, let's start with dark matter. Dark matter supposedly makes up 65% to 69% of that supposed 95. The very first concept of dark matter came from this guy, Lord Kelvin. In 1884, using mass calculations, he came to the conclusion that many of our stars, perhaps a great majority of them, may be dark bodies. Throughout the following century, dark bodies evolved into dark matter. Now, scientists need dark matter for a variety of reasons. However, the main reason it's been theorized is that galaxies are just too well put together. There simply aren't enough things in a galaxy to keep it neatly contained. According to everything we see in one of these galaxies, it simply does not have enough mass, enough gravity to keep itself together. So we need some other form of matter, some form of matter which as yet remains invisible. It doesn't reflect, refract, or absorb light. However, light does play a crucial part in detecting this dark matter. It proves its existence through something called gravitational lensing. Now, gravitational lensing is part of general and special relativity, and that is a whole other can of worms and another video. But the basics are this. Light travels across a straight line in space. Large gravitational bodies can bend space and bend a light path. This is most effectively seen with black holes, where you see this really cool warping effect around the event horizon. So this effect of gravitational lensing has been found in galaxies and star clusters. Far more gravitational lensing than should be there, because there's just not enough stuff to make light bend that way. So there has to be some kind of dark matter, some matter we cannot see but still affects our galaxies. Now, there are lots of theories as to what dark matter actually is, and I won't be going over them, but it should be noted the great names that astronomers and physicists have come up for them. Now we come on to dark energy. Dark energy makes up about 30% of our pie chart, and dark energy works on a much larger scale than dark matter. While dark matter helps facilitate the structures of galaxies, dark energy helps facilitate the structure of our entire universe. Essentially, dark energy helps with the expansion of our universe. As you know, about some 14 billion years ago, the universe began to start. The Big Bang created space, time, and everything in between. Now, the problem starts with the speed it expands. Since the universe expends energy as it expands, it makes sense that that expansion would slow down, since the residual energy from the Big Bang would be used up by making more space. So imagine the shock of astronomers when they discovered that one, not only was the universe expanding, it wasn't slowing down. The expansion wasn't constant either. The universe was actually speeding up. Its expansion was getting even faster. Our universe is getting bigger and bigger at a faster rate. Something needs to be pushing it. And so we have dark energy. Now, dark energy originally started with Einstein, because of course it did. Einstein's field equation for general relativity related gravity, mass, energy, and all their interactions. So he solved for masses on Earth, and the equation checked out. He solved for masses in our solar system, and the equation checked out. Finally, he decided to go big and solve for the entire universe. While he couldn't solve for, the trillions of stars in our universe, he decided to say that the universe had a roughly constant density, if you zoomed out far enough. When he solved it, he was presented with a problem. The total density of the universe turned out to be 0, which meant there was nothing in the universe. Einstein, of course, disagreed, and so he had to somehow fix his equation. To try and fix it, he added the cosmological constant, which would stabilize the equation. Instead of the total density being 0, it would turn out to be proportional to our new constant. Einstein reported that for the constant to work, empty space takes the role of gravitating negative masses, which are distributed all over the interstellar space. A rather fitting description of dark matter. There's also something a little strange about dark energy that's worth mentioning. Matter scales cubically, meaning if you have a cube and make it twice as large, the density of the cube will decrease, and it decreases by the third power. If you scale the cube by 2, then the density decreases by 2 to the power of 3, or 8. If you scale it by 3, then the density decreases by 3 to the power of 3, or 27. Now radiation scales to the power of 4. Not only does it scale in three-dimensional space, but it undergoes some redshift as well. Now redshift is a topic for another video, but basically if you take the space some light is in and stretch it out, the wavelength of the light decreases. Dark energy doesn't scale. Since it's an intrinsic part of space, it just scales with space. The density doesn't change. It's very counterintuitive, but just something worth mentioning. Space is an interesting place. We don't understand most of it, not for lack of trying, but it's still beautiful to us. Dark matter and dark energy are crucial parts of our understanding, and knowing what they are and more about them will go a long way. We can't say what they are for now, or what their understanding may bring. All we know is that the future is going to be exciting, and I cannot wait.